In this lecture, we'll learn how to balance chemical equations. And before we actually jump into balancing chemical equations, let's learn some of the evidences that tells you that the chemical reaction has been taking place. So the first evidence we'll look at is the formation of the solid, or another way of saying the precipitate formation. When we mix two chemicals in a beaker, and if you see the formation of solid, that means it's in a chemical reaction. In addition to that, sometimes after mixing two chemicals, it may produce a gas, and if the gas is being produced in the solution, it will escape the solution, and you may see the bubbles coming out of the solutions in that case. Sometimes the when the reaction takes place, it either requires energy or it releases energy, and in those cases, it will have a temperature change of the solution. So if the temperature goes up for the solution, that means the energy has been released after the reaction takes place. If the temperature of the solution goes down, that means the reaction required an energy and it retrieved the energy from the solution. Sometimes you may not see a temperature change, but that doesn't necessarily mean there is no chemical reaction. Any one of those evidences will tell you that there isn't a chemical reaction. You don't have to have all of those at once. You may have only one, and that's it. The next one is a color change. Sometimes when you mix two chemicals, there is a sharp color change, and that tells you it's in a chemical reaction. We can also see composition change in some reactions. For example, if you burn something, it turns into an ashes, so that's a change in that's the change in the composition. And when you're burning something, it's also producing a lot of energy, so that also tells you it's in a chemical reaction. You may see the change in the odor for some of the chemical reactions. So if the smell changes for a chemical reactions, or all of a sudden if after mixing two chemicals the smell comes out, that means it's forming some sort of gas, and that gas is being observed in the form of odor in that particular case. So those are some of the evidences you will see in a chemical reaction. Okay, now let's talk about how you're going to be using the laws of conservation mass and balancing the equation. So laws of conservation mass usually says whatever amount you have in the reactant, it should not exceed when you're making the products. Or another way of saying, if you have 10 grams of the reactant and all the reactants has been converted, the amount of product should only be 10 grams, and it's not going to be more than 10 grams. Or another way of saying, you do not create or destroy the mass when you're doing chemical reactions. So that's why it's important to balance these equations. And when we're balancing the equations, you have to make sure the number of atoms of the same element are same on both sides of the equations. So before we get into that, let's look at this generic reaction where I have A2G, and that's in the gas form, plus B solid is making A liquid plus AB2 aqueous. All right, so you will see two sides of the chemical reaction. So the first side is going to be called the reactant. So this is the reactant. And the right side is going to be called the products. So in this case, you can see you have two reactants and you have two products being made at the end of the day. And the arrow tells you the direction of the reaction. It tells you it's going from the left to the right, and wherever the tail of the arrow is, that side represents the reactants, and wherever the head of the arrow is, that side represents the product. Okay, so then in addition to that, a lot of these reactant species or even the product species will have some sort of phase. For example, in this case, the G stands for the gas. That means the A2 in this particular case is in the gas phase. This B has the S in there, that stands for the solid. And then this A has L with it, that stands for the liquid. And AQ stands for the aqueous solution. So you want to be aware of these different phases. Aqueous means it's dissolved in water. All right, so I just randomly have all four phases in this particular reaction just to kind of make sure you're familiar with how they're going to be written out in the reaction. Okay, so in addition to that, if you see a number at the right after the reactant or the product, like in this case, this 2 right there, this is called a subscript. All right, so another subscript here is going to be this 2 right here. That's also a subscript for that particular product, which is AB2, and the numbers you usually have in front of the reactants and the products, so like in this case, I don't really have any numbers written in front of these reacting species in the products. Those are called the coefficients. So these numbers that we're going to have here are going to be called coefficients. If you don't see anything written on it, it just automatically means there is 1 in front of them. If you have any number other than 1, you must show that. Okay, so when you're balancing the equations, you have to make sure the elements or the atoms of the same elements are same on both sides. And when you balancing those, you never mess with the subscripts. You don't change the subscripts. You're only going to be playing with the coefficients numbers so that you can have the equal number of atoms on both sides. Okay? Anytime you change the subscript, for example, if I try to make this A2 to like A3, then you're actually changing the chemicals. So don't change the subscripts, only change the coefficients. Now, there's a couple of things you can always do when you balance equations, and this is like a little bit of just in a generic example, but I'll take in a real example. If I see I have 2 A's on the reactant side, okay, and I got 1 B on the reactant side, and on the product side, if I count how many A's I have, I got 1 A here and I have 1 A here, so that's already a total of 2 A's here. And that's what you really have in the reactant side. Okay, so that means your A's is already balanced, so you don't need to do anything to the A. But when you look at the B, there are 2 B's on the product side because it says AB2, so this 2 belongs to the B. All right, so you got 2 B's on the product side. All right, and on the reactant side, you can clearly see there is only 1 B. So since you have only 1 B, you got to somehow make 2 B's on the reactant side. And like I said, don't do something like this. Don't put a 2 on the subscript of the B. That will change the chemical. But instead, go ahead and put a 2 as in a coefficient. So that will change, that will balance the B in that case. You don't necessarily have to write out what the elements on the reactant side and on the product side to balance the equations. I usually balance the equations without writing it out, and there's a couple of tricks you can always follow, and they work almost all the time. All right, so let's look at an actual example. So suppose I have this CH4 reacting with O2, and it's going on to make CO2 plus H2O. All right, so they are all going to be in the gas phase in this particular case, and you will be given in a complete reaction where you actually have to balance it. So when you look at the number of carbons, they may not be the same, and the oxygens, they may not be the same on both sides. Now, 2 things you always want to keep in mind when you're balancing equations. The first thing is always balance the atom that has the highest subscript. All right, so that usually works pretty well most of the times. Okay, and then the second thing you want to look for is balance the atom that's by itself at the very end. All right, so in this particular case, the first thing we said, balance an atom that has the highest subscript, which is going to be 4, which is going to be the hydrogen here. And then balance, when we're looking at the hydrogens, how many hydrogens you have on the reactant side. We have 4 hydrogens. And how many hydrogens you have on the product side? We have only H2O. That means there's only 2 hydrogens. So what would you do to balance the hydrogens there? Well, I can go ahead and put 2 there. Okay, so when you do that, the hydrogens are balanced. Now let's focus on the carbons. How many carbons you have on the reactant side? I got 1 carbon here, okay, and I got 1 carbon on the product side. So your carbons are already balanced, so you don't have to worry about balancing the carbons, okay. And remember, I said leave the element that's by itself, whether it's on the reactant side or on the product side, until the end to balance it. So the oxygen, we have it by itself, so that's why I didn't really balance it until I have every other element balanced, okay? So now when it comes down to balancing this oxygen, now let's go on to the product and figure out how many oxygens you got here. So I have 2 oxygens here on the CO2. And on the water, how many oxygens I got? Well, I have 2 oxygens as well. So that's a total of 4 oxygen atoms here. So that means you got to make sure you have 4 oxygen atoms on the reactant side, and that's we can do that by just putting 2 in front of the O2. So that's going to be a complete balanced equation for you. Okay, let's take another example that's going to be maybe a little bit complicated. Suppose I have C8H18, that's the active ingredient in gasoline, that's octane. When it's burned in the presence of an oxygen, it obviously makes carbon dioxide and water. Okay, now let's try to balance this equation. So we're still going to be using the same drill, okay? Focus on the atom that has the highest subscript, okay? So the highest subscript you got in both of those sides is going to be the hydrogen. So hydrogen has 18, and then you have carbon, all right? So those are the 2 elements I have here that has the highest subscript. So worry about balancing the hydrogen first, okay? So since I have 18 hydrogen on the reactant side, I need to have 18 hydrogens on the product side. So what would I have to put in front of the water to make 18 hydrogens? Well, you already have 2 hydrogens in water, so if I put 9 in front of H2O, that will take care of the number of hydrogens there. Okay, so that's the hydrogens now. Let's focus on your carbons. I have 8 carbons on your reactant side. And how many carbons you have on the product side? Well, so far we have only 1 carbon on the product side. And to make a total of 8 carbons on the product side, I can go ahead and put 8 in front of CO2. And that takes care of the number of carbons there. So now you have your carbons and your hydrogens balanced on both sides. And like I said, we will worry about the oxygens at the end because oxygen was by itself. Now, focus on how many oxygens you got on the product side. So I have 8 CO2, that gives you 16 oxygen. Okay. So maybe I can change the color there. So 8 CO2 gives you 16 oxygen here. And then plus how many oxygens you have on the water. I got 9 water molecules, so that's going to be 9 oxygens there. So that's a total of 25 oxygen atoms there. Okay, so since you have 25 oxygen atoms, I need to go back and make sure I have 25 oxygens on the reactant side. And since you already have 2 here, what number would you put in front of the coefficient as a coefficient to make a total of 25 oxygens? Well, the answer is going to be 12 and a half. So go ahead and put 12 and a half momentarily there. Okay, now one thing you want to keep in mind that you don't want to have any decimals or fractions as in a coefficient. Okay, but it's okay to put 12 and a half momentarily, and then we can worry about changing it quickly. So once you go ahead and put 12 and a half, now you need to worry about changing into a whole number. So think of a smallest integer that you can multiply 12 and a half with so that you get a whole number. Well, since it's in a half of the number, you can multiply this by 2. So to be consistent, you have to multiply this whole reaction by 2. Okay, so when you multiply this whole reaction, it will balance out by itself. So I got, then I would have, let me just copy this down here. Okay, so I can clearly see how I got, when I multiply everything by 2, I would have 2C8H18, and then this 12.5 is going to change to 25, and then this 8 is going to change to 16, and then this 9 is going to change to 18. So that's going to be your final balanced equation where there's no fractions and no decimals as in coefficients. Everything is in a whole number. Okay, let's try one more. Assume I have Na3PO4 aqueous reacting with COCl2 aqueous, and it goes on to make CO3 PO4 2 solid and NaCl aqueous. Okay, so let's worry about balancing this equation, and let's see, we don't really have any element by itself, so let's focus on the atoms that has the biggest subscript. So one of the atoms I can see that has the biggest subscript in there is obviously going to be the oxygen here. All right, so how many oxygens we got here? And the PO4, you have 2 outside, so that gives you 8 total oxygen atoms there. Okay, and you got to make sure you balance the oxygens, but in addition to that, hold on to worry about the other big subscripts as well. The other big subscript you got here is the cobalt. That gives you 3 cobalts here, and we can worry about balancing that as well. Now let's go back and focus on the oxygen first. So you got 8 oxygens on the product side, and now when I go back onto the reactant side, how many oxygens I have? The only source for the oxygen is the sodium phosphate, or the first reactant, which actually gives you 4 oxygen atoms. So to make 8 oxygen atoms, what would I have to do? I would go ahead and multiply this reactant by 2. So put 2 as a coefficient in front of sodium phosphate. Okay, now let's worry about balancing the cobalts. Okay, so when you're balancing the cobalt, you have 3 cobalts in there, and when I'm looking at my reactant, the cobalt source is going to be COCl2, and there is only 1 cobalt so far. So since there's only 1 cobalt, I can go ahead and put 3 in front of cobalt chloride, and that will take care of the cobalts. Then finally, let's look at other atoms now. Let's look at the sodiums. Okay, so on the reactant side, how many sodiums I have? Well, I got Na3, but there's 2 in front of it, so that's going to be 6 sodium atoms. And when I'm looking at my product, the only source for sodium is going to be this NaCl, and right now it's got only 1 Na. So to make 6 of those, I would have to go ahead and put 6 in front of NaCl, and that takes care of the sodiums. Now let's worry about the chlorine as well. You got to make sure you check every single element for their balancing. The chlorine here, I have COCl2, but there's 3 in front of it, so that's going to be 6 chlorine atoms there. And when you have 6 chlorine atoms, on the product side, there is 6 in front of NaCl, so that makes it 6 chlorine atoms as well. All right, so that's your balanced equation. Everything is balanced in this case. All right, so hopefully this video was helpful. If you have any questions, feel free to leave any comments in the section below.